Today's lesson, we're going to be expanding expressions using the distributive property. So today's learning target is I can expand expressions by applying the distributive property. The distributive property is not something new. It's a concept that's taught in elementary school and then in 6th grade most recently. And now when we get into 7th grade, we're still going to be talking about distributive property, but we're going to be looking at it in kind of two different lessons. And so in the first lesson, we're going to be expanding expressions. And this is something that you've been taught in previous grade levels. It's the one that's probably the most familiar, which is why I like to start with it. When we go to expand expressions, we often like to use area models, specifically the area of rectangles, to kind of help explain this. So if you look at the first problem, it says two students are finding the area of the large rectangle. See below. And the first question just says, explain each student's work to find the area of the large rectangle in words or annotate the rectangle drawing. So in student A, you can see that they essentially took, we're going to call 4 the length. They essentially took the length and they multiplied it by the width. So the width now is something that you can see. It's the length of the first small rectangle is 8 and the other one is 10 for a total of 18. So you can see in their work that they did just that. They did 4 times 18 and got the area to be 72. So they kind of saw it as a product, meaning that they were looking at their length times their width, kind of the traditional way to find the area of a rectangle. Now, student B also was thinking in terms of length times width. However, if you look closely, they didn't add 8 plus 10. What they actually did was they found the area of this first rectangle to be 4 times 8, which is 32. So the area here would be 32. And then they decided to find the area of the second rectangle. And you might be saying it's missing a length, but the length is shared, meaning it still has a length of 4. It's 4 here, it's 4 here. No matter where you kind of run across there, it's still going to be a length or a height of 4. And then the width is 10. So to find the area of this part of the rectangle would be 4 times 10, which is 40. So this whole area is 40, or 4 times 10. So if you take those two areas and add them together, it's going to give you the area of the big rectangle. So they were kind of thinking about it as taking the length times the first width plus the length times the second width. So they were kind of looking at it as the sum of two smaller areas. So they're kind of adding two smaller areas together, whereas student A was kind of just doing the traditional take the area of the big rectangle. So this problem hopefully might have been familiar from something that you did in 6th grade with the distributive property, working with numbers and looking at how they can kind of divide different parts of a rectangle and kind of different strategies to approach it. So now, the big question that we have is, what if part of the rectangle isn't a number yet? So that's kind of when we get into 7th grade, you're going to start thinking about expanding expressions that have variables and that have positive and negative terms. So when you look at this problem, you now see that there is still a common length of 4. There's still a common length of 4, but now you see that the widths that they give you are 2x is the first small width, and then the next width is 10. So the length, use a different color, the whole width is 2x plus 10 if I was to use the length of the entire big rectangle. So the second question is similar to the first, which says, hey, there's student A's work, student B's work. Which student is correct? Are they both correct? Explain each student's work to find the area of the large rectangle in words or annotate the rectangle drawing. So now when you're looking at a rectangle that doesn't have numbers for all of its dimensions, it just gets a little bit more complicated. And so when we look at student A, you can see that they did similar work to what they did in the problem above, which is that they did the length times the width. So they still thought about it as a product, right? They still thought about it as multiplication, okay? They thought about it as a product or the area of the big rectangle. Excuse me for kind of writing on the side. And then if you look at student B, they also did something similar from what they did above, which is they took the length of a smaller rectangle and multiplied it by the width of one of those smaller rectangles. And then they essentially repeated that. They took the length of the other smaller rectangle and multiplied it by that width. So they did 4 times 2x, and then they did 4 times 10, and they added them together. So same idea as before, they were thinking about this as a sum of 2 smaller products or area. So student B essentially took the areas, so 4 times 2x is 8x, and then they did 4 times 10, which is 40. So they took the area of the 2 smaller rectangles and added them together. And that should give you the area still of the large rectangle. So they're definitely both correct. They just look a little different. So student A says the area is 4 times 2x plus 10. So they did like a width. I keep wanting to say width. They did a length times the width of the big rectangle. Whereas student B said, hey, no, it's 8x plus 40, meaning it's the length times the first width plus the length times the second width. So 2 different ways to be thinking about this problem, but both are correct. And this is kind of setting us up for jumping into how do we do this skill-based expanding expressions. What is all this going to mean on the next page here? So on the next page, it just kind of has a cleaner version of what we kind of discussed on the first page, which is this idea of the area of the big rectangle can also be thought of as the sum of the areas of the small rectangle. They're both equivalent. And so the length times the width of the large rectangle is equal to the length times the width of the first smaller rectangle plus the length times the width of the second rectangle. So both of these are equivalent expressions. They both can represent the same problem, okay? So, but what does it mean to expand? So essentially when we expand an expression, we're given the product or the area of the big rectangle, and we're going to rewrite it as the sum of the smaller areas. So essentially, if you look at the picture, we're going to be given our problems that look like this, and this is going to be essentially our answer when we expand. Okay, so let's look at what that looks like with an example below. So in our example, we have -3 times the quantity 4x plus 2. So now throwing in some negative terms because we definitely are going to see those in our example problems. So we're trying to see what that is equivalent to. We're trying to expand this expression. So step 1 says identify the factor outside the parentheses. So when I look at the factor outside the parentheses, I see a -3. It's important still with this lesson as well as my lessons prior, that you keep the sign with the term. And step 2, multiply the outside factor by each term inside. Don't forget to keep the sign with the term. So I need to identify my terms inside my parentheses. And I'm going to go ahead and just kind of circle them to kind of help you see the different terms. So our first term in the parentheses is 4x. And our second term in our parentheses is positive 2. So however many terms are in our parentheses are also how many terms we should have at the end after we expand. So step 2, we're going to multiply each term by -3. So essentially taking this -3 and we're multiplying it by both terms inside the parentheses. So we're going to take -3 and multiply it by 4x. So -3 times 4x is -12x. And then I'm going to take -3 again, but I'm going to multiply it now by the second term, which is 2. -3 times 2 is -6. So now I'm going to rewrite the expression as a sum of the products. Now, I know it says the word sum there, but really, if you watched my combining like terms video, we always keep the sign with a term. And so our first term is going to be -12x. And now, because it says sum doesn't necessarily mean we're going to use an addition sign. If you notice, the product of my second term was -6. And so this negative sign can also act as a subtraction sign. So if this is a positive 6, I would write +6. If it's a -6, which it is, I'm just going to write -6. So my final expression is going to be -12x minus 6. So now we're going to move on to the 4 we do problems we have. When we're done with these, you are going to have 4 more you do problems to do after. So notice here we have the area models over here. So they are there for you to use, and I'm going to use them. Area models are a great way to kind of organize your work, to understand when we're expanding an expression, kind of what parts of the rectangle we're talking about. So I'm going to definitely use those in these examples. And so when we look at the first example, we have 3. Okay, so 3 is going to be our length. So that's going to go there. And then my terms inside, I have K. That's going to be my first width. And then my second term is -4, which is essentially going to be my second width. So now when I expand an expression, remember I'm talking about I'm given the area of the big rectangle, 3 times the quantity K minus 4. And now I'm rewriting it as the area of the 2 smaller rectangles. So I'm essentially taking my length 3 and I'm multiplying it by K and I'm multiplying it by -4. So 3 times K is 3K. And then this is also 3. So 3 times -4 is -12. Now, so the area of the first rectangle is 3K. The area of the second rectangle is -12. And so when I rewrite it, I'm going to write on my line that's 3K minus 12. So seeing again how the area and how the algebra version kind of works together. So again, let's look at the next example. -2 is my length. My first width is, I'll use green to stay consistent. 2x is my first width. And then my second width would be -9, always keeping the sign with the term. So essentially I'm taking that -2 and I'm multiplying it by each term in the parentheses. So I get -2 times 2x, which is -4x. And then I'm doing -2. You can put the -2 over here. -2 times -9 would be +18. So here are my 2 areas, and I'm writing them as a sum. So the area of the big rectangle would still be negative 4x. And here's where I'm going to write plus 18. So remember, this is a positive 18. And so you're going to write plus 18 to show that that's a positive 18. So remember, it's a sum of the two terms. So if that second term is positive, you're writing plus that term. If the second term is negative, you're subtracting that term as you see it. All right, the next example is a fun one. You see a negative sign outside the parentheses. So when I put this negative sign here, you can kind of think about it two different ways. So I'm going to go ahead and circle my other terms in the parentheses. So I have 10y and positive 5. So I'm distributing this negative sign to the two terms in parentheses. So you can think about this as kind of one of two ways. You can think about this as subtracting every term in the parentheses, meaning that if I'm subtracting positive 10y, that would be negative 10y. If I'm subtracting positive 5, that would just be minus 5. Now, if you don't want to think about it as multiplication, like we've been thinking about it, that negative on the outside is really like a negative 1, meaning that you're multiplying everything by negative 1. So you're not actually changing the number per se, you're just changing the sign of the terms in the parentheses. So when you set up the area model, you still would have 10y there, and then your positive 5 over on the right. You don't need to write plus 5 because it's already a positive 5, but feel free to write it there if that just helps you. And then when you go to multiply, you get negative 1 times 10y, which is just negative 10y. And then you get negative 1 times positive 5, which is just negative 5. So when you're multiplying by negative 1, you're just changing the signs of what's in the parentheses. And you can also think about it as just subtracting everything in the parentheses, which also just changes the sign. So either way, you can think about it as subtracting everything in the parentheses or thinking about that negative actually being a negative 1. I have some students who also kind of rewrite the problem here. I'll write it over here, negative 1 times 10y plus 5, and that can kind of help them understand that there's actually a negative 1 there outside the parentheses. So I wanted to make sure I threw in that example because sometimes those are the ones that kind of trip people up. So let's look at the last example. We have a 7 on the outside. So that's going to be my common length. And then I have my first term is 9a. So that's my first width. My second width is going to be negative 7. And so when I go to multiply, I'm going to take 7 and multiply it by 9a, which is 63a. 7 times 9 is 63. So it'd be, 63a. Then I'm going to take that 7 and multiply it by negative 7. 7 times negative 7 is negative 49. So I'm going to go ahead and rewrite the area of the big rectangle as the sum of the area of the two smaller rectangles, which is 63a minus 49. So remember, when you're looking at all these problems, they're all equivalent, meaning that when you're expanding an expression, you're not changing the value of the expression. You're just writing the area in a different format. And it might not make sense right now why we're doing that, but I promise you, as you move forward in math classes and courses, you'll understand kind of the importance of or the benefits of a problem being in one format versus the other, meaning in expanded form or factored form, which is going to be the next lesson. So if you go down to the you do problems, there's 4 more for you to try. Please do your best. Don't forget to keep the sign with the term. Thanks so much for watching, and good luck.